Billahi Rajim. Bismillahir Rahmanir Rahim. Dear students of class 12th, our topic is Gauss law in magnetism and Earth's magnetic elements. Magnetism, as you know, in electrostatics, Gauss law states that the the surface integral of electric field over a closed surface equal to 1 by epsilon naught times the total charge enclosed by the surface. That is mathematically E surface integral E dot ds is equal to q by epsilon naught. In magnetic flux, we define the number of magnetic field lines that pass through a surface held normal to the field. This magnetic flux is a scalar quantity. Its unit SI unit is Weber, and Gauss' law states that the surface integral of a magnetic field over a closed surface is zero. That the net magnetic flux through any closed surface is always zero. That is surface integral of B dot ds. B dot ds is zero. In electrostatics, it is E dot ds is equal to q by epsilon naught. This is one of the equation of Maxwell's equation. One of the equation in Maxwell's. Let us consider a Gaussian surface, any closed surface that encloses one of the poles of a magnet. The number of field lines, the number of that dashed line, that is the Gaussian surface, it encloses the magnet. So number of field lines entering the surface and leaving the surface, they are equal. So total magnetic flux is zero. Gauss' theorem implies that there no isolated poles can exist. And if the surface is open, then B dot ds is equal to pi b. That is magnetic flux. Characteristics of Earth's magnetic field. We know that Earth is considered to be a huge Bohr magnet, and it has its own field. And the presence of field can be felt that when we suspend a Bohr magnet, it points always in the north and south direction. And now we have three important elements. We call that geographic meridian, magnetic meridian, and angle of declination and angle of inclination and dip. We define the term geographic meridian. It is a plane. It's a vertical plane passing through the geographic north-south. It contains the longitude, circle, and axis of the rotation of the Earth. So you see that A, B dash, C dash, D. A, B dash, C dash, D. It's a vertical place which passes through the geographic north-south. So that is, since the magnetic field, south and north, they are inclined to the geographic north-south. They are not in the same direction, and also they are always in the opposite. Geographic north and magnetic north, they are in opposite direction. So, and they are not in the total opposite, but are inclined at some degree, that is around 11 degree. That is, if we draw a plane through the magnetic mirror, that is geographic magnetic mirror, the magnetic north and magnetic south, the line joining or the plane passing through the magnetic meridian is called magnetic meridian. Geographic is the vertical plane which passes through the geographic north-south, and magnetic meridian is the vertical plane which passes through the magnetic north and magnetic south. So it is a vertical plane through north-south line of freely suspended magnet. Now a magnetic declination. It is angle. Declination is the angle between the true geographic north-south direction and the north-south line shown by a compass needle at a place. So the line geographic north and the line along which a magnetic suspends at a place. So the angle they make, that is angle of declination. That is angle of declination. The value is more at higher latitude and smaller at equator. The declination in India is small. It is 0 degree 41 minutes east at Delhi and 0 degree 58 minutes at Mumbai. It means that here compass needle tells us true north quite accurately. So that means the needle at Delhi or Mumbai, they point towards the actual north-south portion. Magnetic inclination or dip. Magnetic inclination or dip. It is the angle between the axis of needle which is free to move about a horizontal. The dip is angle that the total magnetic field of Earth makes with the surface. Dip is 0 at the equator and it is maximum at poles. It is denoted by delta. Figures you see. If the angle between the total, total magnetic field and the horizontal component is called dip. It's called dip. You see the figure. AB is the magnetic meridian or horizontal. Plane ABCD is magnetic meridian. AB is the horizontal and AP is the total magnetic field Earth. The component of this along AB is called horizontal component BH, and component along vertical, that is AM, is called vertical component denoted by VH. VH. So we see from the triangle APL. APL cos delta is AL by AP, and AL, hence AL is equal to AP cos delta, that is horizontal component of Earth is B naught and cos theta. The component of Earth magnet along the vertical will be sine delta is equal to LP by AP, that is LP is equal to AM is equal to LP by AP, so it is B naught sine delta square, and adding we get B square, BH square is equal to BE square cos square delta, and BY square is equal to BE square sine square delta. So square adding, now we will get BH square plus BY V square is equal to BE square. So BE is equal to root of, so total magnetic field is root of BH square and B square. The relation between horizontal component and vertical component, angle of dip. Dividing the horizontal component, vertical component by the 100 will be BV by BH is equal to B E sine delta over B E cos delta. So it is BV by BH is equal to tan delta. So this gives the relation between horizontal and components. Earth's magnetism. As again we know that when Earth when put a magnet, when the power magnet is put on the table, we will see if we mark the magnetic field aligners, we will note that there are some area or pointers where the magnetic field is zero. You can see the magnetic, and then if the magnet is placed with north facing south, then one type, then the neutral pointers, we call them neutral pointers. While there is no magnetic field or that needle does not show the deflection, we call that neutral pointers. So we define neutral pointers. It is a point where the magnetic field due to a magnet, Bohr magnet or a coil is equal to the and opposed to the horizontal component of the Earth's magnet field. But at each and every point, the horizontal component is equal to the magnetic this field due to the Bohr magnet. As horizontal component is from magnetic south to magnetic north, field due to the magnet should be from north to south. Now when magnet is held with north pole facing the held with north pole in the direction of the magnetic south, then the pointers lie equidistant from the poles and on the axial line, and magnetic field is equal to mu naught 2m by 4 pi r cube. Mu naught by 4 pi 2m by r cube. When the north faces the magnetic north, then the neutral points are found on the axial equatorial line, and their field is equal to mu naught 4 pi m r cube. If a magnet is held vertical, then there will be only one neutral point.